their lives as clouds of gas and dust known as
nebula.
Thank you. Rachel.
Protostar.
Rachel.
10 million degrees Celsius.
Rachel again.
Helium.
Thank you. Rachel.
Main sequence.
Yes, thank you.
Hey girl, did you hear the stars are dying?
What? Which stars? Probably from drugs, right?
No, not those stars. The stars in space.
How in the universe did those stars die?
Well, it depends primarily on their mass. Take it away, Rachel.
I'd love to, Shannon.
Average stars are those roughly the size of the Sun. Red giants form when those main sequence stars run out of hydrogen fuel. As the star cools and contracts, it is able to form a new fuel, helium, and rapidly expand. As red giants become unstable, they may expel their outer atmosphere, creating a cloud of gas and dust called a planetary nebula.
So, what happens to a planetary nebula?
As the outer shell continues to drift away, the dense core remains and becomes a white dwarf. It is made of extremely dense, degenerate matter, which cannot be compacted any further. White dwarfs are usually only slightly bigger than the Earth, but are 200,000 times as dense. In 1863, telescope maker Alvan Clark spotted a mysterious companion star to Sirius. This was later determined to be the first seen white dwarf. The orange soccer ball represents an average star, which tends to be about 1 solar mass. It is easy to catch. The little silver ball represents a white dwarf. Though many times smaller in size, their mass is comparable to the Sun and is therefore hard to catch.
Oh, okay. But what about bigger stars?
Massive stars are those that are at least 10 times the size of the Sun. When they run out of hydrogen fuel, red supergiants form in the same way as red giants. The only difference is that they are much larger. When fusion of helium ceases in supergiants, the core collapses and heavy elements such as carbon begin to fuse. This type of fusion releases so much energy that the star blows itself apart, hurling material into space. What is left is a dense core of iron. The energy released during this time period often equals the energy radiated by normal stars over their entire life. Our physics teacher, Dr. Laney, helped us demonstrate a supernova explosion by filling a container representing the surface of the star. In this experiment, he mixed hydrochloric acid and zinc to create hydrogen gas. The gas then ignited, causing a rapid expansion beyond the container's surface. This explosion represents the energy released from the fusion of carbon in a supernova. After the supernova, the core collapses. Protons get crushed with electrons, forming neutrons, hence neutron stars. They are about 10 miles in diameter and more massive than the Sun, making them the densest of all stars. The balloon represents a massive star. It expands and turns into a red giant. Then it goes supernova and material flies away, leaving the dense neutron star core.
Do supernovas always turn into neutron stars?
If the star is massive enough, some 20 times the size of the Sun, the star turns into a red giant in supernovas. The core that remains is so dense that no internal force can push against gravity. It compacts into a mathematical point with infinite density. Not even light can escape. In 1916, Carl Schwarzschild predicted the existence of a dense object that objects could fall into but never come out of. The term black hole was coined by John Archibald Wheeler in the 1960s. Gravity changes rapidly when objects approach a black hole. The closer the object is, the stronger the gravitational pull felt by the object. Spaghettification occurs as the part of the object closest to the black hole is pulled more strongly than the part of the object that is farthest from the black hole. Eventually, the front of the object is pulled so far from the back that the object begins to resemble a spaghetti noodle.
Guess what?
Oh, what?
Did you know that during a star's life, many different factors can determine their eventual fate?
No, I really didn't.
Well, nuclear fusion plays an important role in the life of the star, but usually the star's size is the key to their eventual end. The size and density predict whether the star becomes a dwarf, a black hole, a nova, a supernova, or a neutron star.
Rachel, you're such a nerd.
Let's surf into space.
Louder.
Ah, I can't scream it.
Scream it.
Scream it. Let's surf into space.
Where's these dying stars? Ew.
It's so dirty.
Here, baby, get up there.
No.
Do it.
No. Look at that. A supernova. Oh. A supernova